So it's a pleasure to have Nick Rod from Berkeley here with us today. Nick, usually the seminar is a little bit over an hour, but at an hour you can give people a chance to ask questions. But don't worry if it goes too much over. So please go ahead.
Awesome. Yeah, thank you. I'm very happy to be here. So what I want to use my time today is to tell you about how you can calculate the spectra if you have very heavy dark matter. So what I have in mind here is that, let's say the dark matter of our universe is like some very heavy particle. Then if it's out there, one way we could detect it is if this particle can decay, it can then undergo some large showering and hadronization process, like I'm showing you in the center of the slide here. You'll get some spectrum of stable, say, photons or neutrinos, and these are the particles you can then go and look for and hopefully correlate it with dark matter and eventually make a discovery. So this is something that's been known about for quite a while, but what I want to tell you about for today is some recent work I did with Christian Bauer and Brian Weber that came out in this reference at the bottom of the slide, where I think for this heavy dark matter case, we significantly improved upon the predictions for what those spectra should look like. So as I'm sure everyone here is aware, these days when we talk about searching for dark matter, we're really thinking about some enormous parameter space. So let me be slightly more quantitative about what I mean when I'm saying heavy dark matter, because that's just sort of maybe telling you whether I'm heading left or right on that mass spectrum. And in particular, when I say heavy, I mean particle dark matter with a mass between the TeV and the Planck scale. So we're going to be looking over a huge number of orders of magnitude where we're interested in calculating these spectra. And our results that, as I'll show you at the end, are publicly available, will allow you to produce those spectra over that range. So before going into the details, let me just sort of give you, a short version of the full story. And to begin with, I just want to consider, a very concrete version of the story I want to tell. So let's imagine that the dark matter of our universe is an EeV particle, so 10 to the 9 GeV, and through some operator, it can decay to 2 neutrinos, for example. So then naively, you might think, okay, well then what I should go and look for is sort of a delta function of EeV neutrinos, because that's going to be what the spectrum is. But of course, this isn't the real answer. These neutrinos, they could, at higher order, emit a W or a Z, for example, which can then initiate a cascade of particles that will ultimately result in a spectrum of all the possible stable particles you would get in the standard model. So for example, photons, neutrinos, electrons, positrons, protons, and in principle, even heavier elements as well. So what I want to do is I want to think about this dark matter particle decaying, and I want to calculate in detail what is the prompt spectrum of these states that come out. And just note that I put a qualifier, the qualifier prompt there. So all I'm going to be interested in today is calculating the spectrum that comes out at the location of where this decay is occurring, somewhere out in the universe. That spectrum is not necessarily going to be the same spectrum as what will arrive at my detectors at Earth. The reason for this is because there can be propagation effects. Of course, in the case of neutrinos, there will be oscillations, but also for the other states, there can be non-trivial propagation effects. I'm not going to discuss these in detail at all today in this talk. If you're interested, I refer you to some references at the bottom of the slide here. It's an interesting part of the story. But of course, hopefully you appreciate that a key ingredient, if we're going to figure out what you would eventually see on Earth, is you need to know what you start with. And this is the prompt spectra I'm going to be considering.
But sorry, Nick, can I just ask a question? When you say these propagation effects, these are just, what are they due to? That mean these particles scattering on their way here? Is that what they're taking into account?
Yeah, no, absolutely. And just to give it, because this is a really beautiful story that I'm not going to get into today, but I mean, just to give you some insight here. So of course, for the neutrinos, there'll be oscillations. But if we think about the gamma rays, where I think it's particularly interesting, up around 100 TeV or so, a gamma ray can actually pair create an E plus E minus pair off the C and B. And if this gamma ray is traveling cosmological distances, even if the cross section for doing so is tiny, you've just got so much distance over which this could occur, it almost occurs inevitably. So for extragalactic photons, you do not really expect to see anything above about 100 TeV.
So this is the Schwinger pair production for the 2 photons, right?
I think here it's much simpler. It's literally just, well, I guess it depends on how you think about it. You've got this background C and B. I can just think about this as these, in the rest frame, you have 2 photons annihilating to produce an E plus E minus pair. But there's probably a regime where you can think about this as production of a, an ambient background as well. But that's the way I think about it.
Thanks.
So that's a very interesting part of the story. And I guess just, alluding to something that will come up later, you could say, why would you even look for high energy photons? Actually, if they're produced within the Milky Way, well, then there is a possibility that they will propagate to the Earth, even if they have exceptionally high energies. But there really is an interesting,
Nick, I'm sorry to interrupt, but I wonder, in this way, whatever the origin of this, high energy particles, it should be some signature that it is indeed from the dark matter decay, because the origin of cosmic rays is not known, right? So really, so how I can differentiate between different sources of this particle? So no, I'm sorry. Maybe you are going to tell the story in your way, but just, I mean, it's natural to think about this, right?
Absolutely. No, that's an excellent question. I mean, I can't give you a short answer to this. The answer is it's hard, right? And just to give you a specific example, the IceCube experiment has detected all these very high energy astrophysical neutrinos, and there's a number of unusual features associated with these. And to my mind, we cannot 100% rule out that a large fraction of the IceCube neutrinos are coming from dark matter. But if we're going to do these studies, a critical ingredient in this is you need to know what the dark matter prediction is. And one important part of this is the prompt spectra. And what I want to tell you about today is how you would calculate that. Now, all these details about how you would then go in and understand what's going on here. I mean, if you see an anomaly, it's going to be difficult to know immediately that it's coming from dark matter. I would say maybe one case where you would be confident, if you saw almost a Planck scale photon arriving at your, for example, creating some shower on Earth, I do not think we have any idea of what astrophysically could generate that. So that would probably be dark matter, but anything in between is going to be a more complicated story. That's definitely in the background of everything I'm describing today, definitely.
Okay, thank you. No,
good question. Yeah, so just to sort of give you, what is going to be the answer of, this specific part of the story that I'm talking about today before I go into details. So again, just sticking to this case of this dark matter decaying to two neutrinos with this very high mass, well then, what I'm showing you here is the spectrum for both photons and neutrinos coming out from the prompt decay. And I'm showing it to you in a way that will appear in many of the plots today. So this is the spectra in dimensionless units. I'm showing you the energy fraction of the dark matter carried by either the neutrino or the photon on the x-axis in logarithmic units. And then on the y-axis, I'm showing you the spectrum, or the energy squared weighted spectrum. And again, you can roughly think about this as, what is the probability of producing a photon at this particular energy, essentially, or a neutrino. So you would have thought, as I said, naively, that it would just be a delta function. And of course, the probability for producing neutrinos with nearly all the energy is dominating. But then there is this continuum contribution for photons in orange and neutrinos in blue. And in particular, what I'm contrasting that to here is, before our work, essentially the only way that existed in the literature for computing these decay spectra was to essentially simulate two neutrinos in Pythia at this very high energy and let Pythia handle the showering and decay. And what you can see is that our results are dramatically different. The y-axis here is logarithmic. We're predicting orders of magnitude more flux than what is coming out of Pythia. Now, I'll explain why these details are coming about later on and why I think our results are more accurate. But just to let you know, currently when IceCube is searching for dark matter from neutrinos, they're using the dash spectrum. And so the IceCube collaboration is already actually moving to use our results, but you can already see that there are significant improvements to be made here in these calculations, and that's what we're interested in doing. That said, while I think that our results are a significant improvement, I want to advertise out of the gate that our results are not the final word here. So let me just give you some of the terms and conditions that come with our results if you use them. So we think that at high energy fractions, our results are quite accurate, maybe at the level of 5 to 10%. At intermediate energy fractions, there is an interesting effect that I'll describe called color coherence, which we know has a significant impact on the spectrum, and we only have, honestly, a pretty ad hoc treatment of it at the moment. This is something we'd like to do better, and this could lead to, potentially at intermediate results, maybe quite large errors, up to maybe a factor of 5 or so, that we would like to improve on. And then at the lowest energy fractions, even though I can formally get an answer out of my calculation, I don't trust these at all. For our full calculation, we only have double logarithmic accuracy, and we know that the single log terms we're missing dominate at this lower scale. So I would easily imagine our results could have order of magnitude errors down here. But what's one nice thing about what we're doing here is that for Pythia, it's a bit opaque about what exactly it is and isn't capturing, because it just wasn't designed to operate at EEV energies, for example. But with our calculation, it's systematically improvable. So although there are uncertainties here at the moment, this is something we would like to improve as we go forward. So that's really the story in just a couple of minutes. What I want to do now is just dive into this in a bit more detail. And the way I'll outline the rest of my discussion is as follows. So firstly, I mean, of course, I think most people are motivated that we should look for dark matter wherever we can, but I just want to give you a bit more motivation for why you might want to consider particularly heavy dark matter. And at least I'll give you my motivation for why I spend my time thinking about these calculations. In the second part of the talk, I'll dive into a bit more detail about what exactly the calculation that we did is, where these uncertainties are coming from, and how we plan to improve on them in the future. And then towards the end, I'll give you more results. I've just shown you one particular dark matter mass for one particular channel. I'll run you through a few of the other ones of these later on. And in particular, I'll show you how you can get results all the way to the Planck scale, which I think is a bit of fun.
So in the plot that you did show, like, is the solid and dashed normalized, or is that absolute scale?
I mean, no, these are the absolute scale. You might wonder, how is probability conserved, right? Because if this one is always, if the dashed is always below the blue, the momentum, I mean, or another way, the momentum conservation has to be correct, right? Because essentially what these spectra do is they repartition the dark matter energy around. The way that this is done is in a detail that's not shown in this plot, and that is that there is literally a delta function at x equals 1. And that's corresponding to the probability that nothing happened. There's some probability that you produce 2 neutrinos and they never emitted a W or a Z to start the shower. And this delta function for Pythia is just larger than it is in our results, but it's a challenging thing to plot, so I just haven't put that delta function. So that's how probability, I mean, momentum is conserved in both cases. It's just that the probability of nothing happening is larger in Pythia than in our result.
So that probably means that you're saying they're not improving the sensitivity dramatically in low masses, but rather you're expanding to higher masses.
It depends. Well, sure, yeah, because it depends exactly what you mean. I mean, IceCube at the moment hasn't seen, and I don't think they have sensitivity necessarily to see EUV neutrinos. So this continuum flux is critical for their searches, right? And we're predicting orders of magnitude more. So this would enhance their sensitivity at these ranges. But then if you had a PeV scale dark matter, well then IceCube can see PeV neutrinos. So it would, I mean, it would change things around. It's a mass dependent question there.
Okay, thank you.
And, you know, before you go into details, you know, this is a very typical behavior for PDFs, right? So you're basically calculating the electroweak PDF for the dark matter decay. Is that the way of saying it?
Very insightful, Jeff. Yeah, no, that's exactly what we're all, at some level, that's exactly what we're going to do. I'll phrase it in terms of fragmentation functions, but when I get to section two of the talk, you will see that you've essentially already guessed at how we're going to do the calculation. So that's right.
Sure. Yeah, before going there, let me just ask a few naive questions. First of all, why do I normalize the vertical axis in x squared, not x? Isn't the x the energy? I integrate an area under the curve, I'll get 1. Why do I use x squared?
There's no deep physical reason. It's literally just for plotting purposes. Like if you don't put this x squared, of course, the low energies dominate entirely, right? The low energy fractions dominate. And it's just common, I mean, in the field that I work in, that people often write energy squared when they're plotting this. I think physically there is some nice intuition for using x, as you said, because then you can think about the integrated energy underneath. But this was just for plotting purposes, not for anything else. Yeah.
Okay, good. So another question. Go ahead.
I'm sorry, you said that it's normalized. Normalized to what? So it's a number of events in the interval of x, but I mean absolute number, so or relative number.
Good. Yeah. So what I haven't defined for you here, and I don't believe I have this on my slides, but it's in our paper, is what your question is, what do you even mean by the spectrum? Like that has to be something you can calculate in field theory. And so, for example, for the decay, what I mean is I can calculate the decay rate, and I mean the differential decay rate in energy fraction normalized to the Born decay rate, which is, you know, what we would normally just call the lifetime.
To normalize to which decay rate?
Like the tree-level decay rate, right? So I mean the full decay rate, differential in energy, normalized to the tree-level.
So it does not give you absolute number of events, right? I mean, you still need to know, I mean, how many particles decays or whatever, right?
Absolutely, and that's something that, but usually, I mean, in indirect detection, usually this factorizes into a particle physics factor and an astrophysical factor, because astrophysically we have measurements for how much dark matter is out in the universe, and that will dictate that quantity you're talking about. But this, again, this is just one ingredient for a full story that I've kind of done.
Okay, so just to follow, I just asked.
No, of course, that's right. You're absolutely right. That factor is there, just not in this plot. Yeah. But there was a rigorous notion. There was a rigorous notion of the spectrum I can state in terms of just literally a field theory calculation. I just haven't got it here.
Yeah. And in the PCI calculation, do you use the version where they implement the electric showering?
Yeah, I'll say more about this, but yes, yeah.
Okay. And formally, your calculation is leading logarithmation or beyond that?
It's not even that. It's double logarithmic. Like we haven't got the full. We are just essentially accounting for the double logs, and then honestly, the way we're approaching this, we have identified other things that we know are important, as I'll go into in section 2, and the ones that are most important, we've included some of these, but something that is really what we want to do going forward is do a very systematic leading log next to leading log calculation. We've really just established some of the framework here and included some of the most important pieces. So that's really where the terms and conditions can look to be improved by doing as you say. Yeah.
Okay, thank you.
No, thanks for all the questions. That's good. But hopefully I'll dive into these in more detail as I go through today. Yeah, so let me give you my spin on why I think this is an interesting type of dark matter to think about. So of course, there are UV considerations here where you can think about, well, why would you even believe that the dark matter of our universe could be a very heavy particle? And there's a lot to say on that story. And I know in particular Minnesota, I think that Keith Olive recently has been working on specific models where you can realize extremely heavy dark matter within those. But from my perspective, there's another way of motivating the search here. And that is sort of this principle that we should be looking anywhere we can, because at the moment, we're really not that sure where dark matter should be. Maybe at the moment, you know, axions are sort of the flavor of the month, and there's a lot of good reasons for thinking why they might be the dark matter of our universe. But if instruments exist to search for heavy dark matter, then we should use them, and we should have accurate theoretical predictions for what they should see. And so in particular, I just want to spend a few minutes overviewing for you what is the experimental landscape for searching for these very heavy dark matter particles. And what I want to impress upon you is that I think in the next 5 to 10 years, there's really going to be very exciting data sets that will start to be collected because of new instruments that can search for these heavy dark matter particles. In particular, I want to focus on the search for dark matter using photons. Of course, we can use other channels, and I'll mention a bit about that at the end, but I want to particularly focus on photons. And so in order to do this, let me anchor the discussion using an instrument that I hope that many of you have heard of, the NASA's sort of flagship gamma ray instrument, the Fermi Gamma Ray Space Telescope. So famously, Fermi's telescope can see photon energies around a GeV to a TeV. And so what I'm showing you on the x-axis here is the logarithmic photon energy in GeV. So that's here all the way up to a TeV of about here. What I'm showing you on the y-axis is some measure for how many photons I would expect this instrument to collect for a given dark matter flux. In detail, it's the experimental effective area multiplied by how long it's been collecting photons, or the observation time. So what you can sort of think about this quantity on the y-axis as, it's a bit like integrated luminosity in a collider context. The greater the integrated luminosity for a given predicted theoretical cross-section, the more events I should have. The greater this exposure quantity I'm showing you here, for a given dark matter predicted flux, the more photons I should get from dark matter, essentially. So to try and give you some intuition here, actually there's an easy way to understand why an experiment like Fermi should have an exposure of 10 to the 12. Which is what roughly I'm showing you here. And the way to think about this is well, if I want to see a GeV photon, unfortunately, I have to put something into space. The reason is because when a GeV photon hits the atmosphere, it interacts quite strongly, but the resulting emission that it produces is not bright enough to be seen on the surface of the Earth. So you have to get above the atmosphere to detect it, which means you have to build a satellite. Famously, satellites are expensive. We can't put a kilometer squared telescope into space. The biggest we can hope to get is about 1 meter squared, which is about 10 to the 4 centimeters squared in these units. Further, I mean, realistically, if we want to get the data from this experiment in our lifetime, and so that means we should run for about 10 years or about 10 to the 8 seconds. And so if you're putting something into space in these units, 10 to the 12 is about how well you can do. And this is generically true, even if you go to lower energies. For X-ray experiments, for example, 10 to the 12 in these units is about as well as you can do because you have to put something into space. But what's exciting about going to higher masses is that these photons will still interact strongly in the atmosphere, but the showers they create become larger and larger until eventually you could detect them on the surface of the Earth. And on the surface of the Earth, we can build much larger experiments than we can afford to put into space. So this is something that's been known about for a long time. And so to emphasize, there's multiple different detectors looking for this. And so if we go up to the TeV and higher energies, the experiments that are currently performing gamma ray astronomy in these range, there's many of them, but two of them are, say, HAWC and HAWC. And you can see they do orders of magnitude better than Fermi. And this is just being driven by the fact you can build an enormous instrument on the surface of the Earth. So you can see
the right-hand side of your plots, where it sort of drops very quickly, it's not like you can't detect the photons, you cannot reconstruct the energy. Is that right?
Good. Yeah. So this is a point that is often not really very good observation. And it's a point that is not really drilled into often. If you look at these experimental papers, they often just stop quoting a sensitivity at one point. And I believe that the real issue is that what is not shown on this plot is the predicted astrophysical flux. So remember, what I'm showing you on the y-axis here is the exposure multiplied by the flux tells you how many counts you will get. The fluxes are dropping at, I think at these energies is like E squared. So they're dropping pretty rapidly. And quickly you get to a point where you just never expect to see a photon, essentially. So for example, for Fermi...
Well, it's a separate issue, right? So what I'm saying is that if somebody shoots a 10 to the 6 GeV photon into a Fermi, aperture, you will get some energy deposition, but you probably will not be able to say whether this was 10 to the 5, 10 to the 4, 10 to the 6 GeV.
That's right, but that doesn't mean that their exposure goes to zero because they've still seen something. Right. So, and I'm not even plotting the energy resolution, which is what you're getting at on this plot. But the experiments just generally don't quote anything because usually I think Fermi has only seen up to about a TeV, so around here in photons. They just haven't seen anything up here. So they just stop quoting their experimental sensitivity because I guess it's work to exactly, you need to do Monte Carlo simulations to determine how you could reconstruct such an event. And if they're never going to see one, they just don't bother doing it. So in truth, there's some drop off as you're seeing for some of these, but it is not just a sharp drop off. I'm just quoting, I've just taken these from the experimental papers and at some point they stop quoting them. So exactly how well they could reconstruct this, as you said, it becomes harder and harder, but they don't even try and estimate that because they don't expect to see any photons of that high energy for their given experimental size. Even in the dark matter case, you might predict some of these very high energy photons, but if your experiment is only a meter squared, it's very unlikely one of them will hit it. But that's a good observation. That's what's going on there. Good. So yeah, what I was mentioning is that there are these two types of detectors like the HAWC and the HAWC experiment. It might look here that HAWC is just strictly better than HAWC, but actually sort of getting at what Maxime was mentioning, there are different ways of grading these experiments. So HAWC is going to collect more photons than HAWC, but then how well those photons are reconstructed, actually HAWC will do better than HAWC. So that's why it's making a sacrifice. It'll collect fewer photons, but it'll have better angular and energy resolution for those events. So, I mean, just to give you a bit of an insight as to what the physics is there. So these particles come in, hit the atmosphere, produce this large shower, which will include many charged particles. How HAWC operates is just a bunch of water tanks is what you can see in this image here. And so when those charged cosmic rays go through the water tanks, they'll emit Cherenkov light, which can be detected, and then you can reconstruct the cosmic ray, and then from all of them, reconstruct the original photon is the idea. HAWC operates by those same charged cosmic rays will produce Cherenkov light in the atmosphere or produce optical photons. So on a dark night, particularly you need the moon to be very dark, you can look for that Cherenkov light, and that's exactly what these telescopes are doing. You can therefore reconstruct the shower closer to where it was produced. And so this is partly why they often have better energy and angular resolution, but they really suffer for observation time. HAWC can essentially operate 24 hours a day. HAWC can only operate at night and only on nights when the moon is particularly dim. So this is why they just don't get as much time. So this is what's going on at the moment. And this is essentially, these lines represent data that's already on disk. But what's going to happen in the next 5-10 years is we're going to have enormous improvements on these experiments. And this is why I think this is a very exciting regime to search for dark matter. In particular, there'll be an experiment that sort of upgrades the HAWC way of detecting these showers called LHAASO that is being built in southwestern China. And you can see this is just a mammoth upgrade on this instrument. It can go to lower energies, it can go to higher energies, and it just has a better exposure all the way across. And actually the LHAASO experiment is already partially constructed. And my understanding is that as of late 2019, it was collecting data. So I haven't seen any public works using that data set yet, or any details of it. I just heard about this at a conference. But LHAASO is already collecting data, so we could expect more from that in the near future. And the hope was, of course, current circumstances may have delayed this, but the full array would be constructed in the next few years, and then it would start to collect data set. So this huge experiment that is a big increase over HAWC, is like a big experiment, $200 million, should be collecting data that you will see hopefully in the coming years. So we shouldn't have to wait too long for LHAASO.
Sorry,
First
could you
place.
say what? Sorry, could you say where that's going to be built? This LHAASO?
I'm not exact. It's in southwestern China. So I mean, they have a website where you can look this up.
So somewhere close to Tibet and the Sichuan province, I think. So it's like, you know, Tibet is a really highland, and you know it's a highland plain. I think it's a very good condition, far away from, you know, any big cities and pollution. So it's a natural place to do this. Yeah.
Excellent. Yeah, I didn't appreciate that. Thanks. And I guess just to go back, so here's like an artist rendition is what I'm showing you in blue, but this here is the actual LHAASO, is the image that I showed you at the start. So it's definitely happening. So which I think is very exciting. So then the HAWC way of detecting these showers is going to also have a huge upgrade in the form of the Cherenkov telescope array. So CTA is an array of telescopes. There'll be two arrays, one in the northern hemisphere and one in the south. And what you can see here in this artist rendition of what it would look like is that there'll be many different sized telescopes. So with the smallest telescopes, you can have lots of them and spread them out. And that's how you detect these larger showers associated with the highest energy photons. So CTA can go to higher energies than HAWC. But also actually, it's going to have a number of large telescopes in the center of the array with large collecting areas. And this can be used to detect the dimmest photons. And so this is why CTA can also go to lower energies than HAWC, for example. And actually, okay, so the lower energy side is not so relevant for the talk today, but I also think you can do very interesting physics with the fact that these instruments will give you a huge increase in sensitivity for slightly lower energies. And let me just totally at random pick one example of the physics you can do with that. So I had some work that came out recently where we looked at the perspectives for using CTA to search for another type of dark matter, the thermal Higgsino. So famously, this is a very challenging dark matter candidate to search for. It has a direct detection cross-section below the neutrino floor. It probably could be reached with a 100 TeV collider, but certainly not at the LHC. But the claim is that with some admittedly slightly optimistic assumptions about the dark matter density in the galactic center, CTA would be able to see a signal from the thermal Higgsino, and if it didn't, under those assumptions, rule that out. And actually what was really driving our sensitivity in this work was the lower energy sensitivity of CTA. Because for the thermal Higgsino, its annihilation can also produce a shower of particles like the ones I'll describe today. And the fact that CTA can collect more of those lower energy photons than HAWC was a key contributor to its lower energy sensitivity. So I won't say more about that, but just mentioning that work as well, that these instruments are going to be able to do a lot of exciting physics. Of course, these high energy particles, you don't just have to search for them in photons. You can also look in neutrinos or other charged cosmic rays. So there won't necessarily be big improvements of the like we'll see for photons. But hopefully in the future, IceCube Gen 2 will come online, which will continue to accelerate our search for high energy neutrinos. And then there are also a number of experiments that are looking to eventually improve upon the Pierre-Auger array, which is how we've been looking for some of the highest energy cosmic rays we've ever detected. Like, for example, you might have heard about the proton that was detected with the kinetic energy of a cricket ball. Well, these are the types of experiments that have been searching for those. So because there's this large experimental program that could potentially see a signal for dark matter, the experiments have known about this and they have been looking for it. And so just to give you sort of an overview, what have they been doing to produce the spectra that I'm going to tell you about how to improve their calculation of today? So generally, the instruments that are currently in existence have largely been using Pythia to produce their spectra. And the way that this operates is you just run Pythia where you have like an E plus E minus annihilation, but you turn off ISR. And so therefore, the E plus E minus basically just acts like an energy injection, which is in certain, for dark matter candidates that are uncharged under the standard model, this is what you would expect them to do. And then you let Pythia go to some, for example, two-body final state. It will then handle the showering and hadronization, and this is how you get your spectrum of stable states. But as we saw earlier on, this is very different from what we're going to predict. And I'll say some more words about that in a second. Actually, for experiments that don't exist yet, the collaborations of CTA and LHAASO, they haven't even been using Pythia. They've been using this long acronym, PPPC for DMID, where these authors here, they took Pythia before it had any electroweak corrections in there. They tabulated the Pythia results and manually added in some electroweak corrections. But they only tabulated results up to 100 TeV. So currently these two experiments, even though they concede to much higher energies, don't even look at dark matter masses above those scales because essentially the PPPC tables stop there. So this is maybe not the best reason to not look for higher mass dark matter. Further, if we go to these highest energy cosmic rays like those collected by the Pierre-Roget Observatory, I'm not aware of the actual collaboration doing dark matter searches, but external authors have. And so, for example, these authors here, there's been a number of works, this is just one example, but what they did to get their dark matter spectra was they took some low energy fragmentation function, like the B-quark fragmentation function that's been measured, and then used pure QCD DGLAP evolution to evolve that fragmentation function all the way up to, say, the gut scale, where they imagine their dark matter lived. They used that to get their spectrum out, and then this was how they got their predictions for what Pierre-Roget should see. So of the options being used at the moment, I think that none of these are ideal. So for Pythia, even though it now has electroweak corrections, it does not have all the relevant interactions in the standard model. In particular, the electroweak interaction in the standard model is a non-abelian gauge theory. And so there will be triple gauge couplings, but Pythia just doesn't have any of those in there. And so you can imagine as you go to higher and higher energies, Pythia is going to underestimate the size of the electroweak showers that would develop because it's missing these triple gauge couplings. Furthermore, eventually Pythia just becomes very difficult to run. I mean, it's really predicting way more than we need here. We just want to know that the energy distribution of the stable particles we're searching for. Pythia produces all of the angular correlations as well. That's totally irrelevant for our purposes because you're never going to see more than one particle from these showers, no matter how large they eventually be. If you've got if this shower is produced, kiloparsecs or megaparsecs away. So because of this, it becomes very time consuming to run Pythia at higher energies. And also if you try and run it at an EEV, you can run into numerical issues like Pythia will predict, for example, negative energies. PPPC has a number of the issues that Pythia had, but also practically it just wasn't tabulated above 100 TeV. But there's some nice aspects of this DGLAP approach I mentioned at the end. In particular, you can evolve this arbitrarily high. You're not keeping track of all the angular correlations, which is just essentially wasted information from our purposes. But one shortcoming of what's been done so far is it's only pure QCD DGLAP. If we want to do this, we know that the electroweak effects can be important. And so we need some way of incorporating that into the calculation, but there's something very attractive about the fact that we can evolve arbitrarily high, at least in principle. Of course, the theoretical errors associated with doing so need to be considered. So that's the state of affairs that existed in the literature before our work. What I want to tell you about now is how we did the calculation. In particular, as I'll give you an overview of, we broke the calculation into 3 steps, and really the meat, or sort of the new stuff that was in our work, came in at step 1. So I'll spend most of the time explaining to you what happened there. And sort of the color scheme to guide your eye here is we're doing some evolution from the UV scale in purple of the dark matter down to the IR scale where the stable spectra are produced. So again, let's go back to this example calculation I mentioned earlier of thinking of dark matter decay, and what we want to get is the stable states out at the end. Well, sort of as Jen alluded to, what we're doing here is we're mapping this to something that we know how to calculate very well, or at least there's a large developed literature in QCD. And this is the concept of fragmentation functions. So I'm sure many people in this audience are very familiar with these, but just let me remind you if you're not. So what a fragmentation function is it says, let's say I start out with some particle, J, at some high virtuality scale. Here I'm just, of course, using the dark matter scale, but it could be some arbitrary scale. I want to know what is the probability of producing some other state, or it could be the same state, I, at a lower scale. Here I'm just imagining some low IR scale that I'm labeling 0, carrying a fraction of the energy X of the original energy. So I know that's a lot of words there, but if you think about it for a moment, there are clearly some similarities between what a fragmentation function is and exactly what I'm doing when I'm calculating the spectra of these particles here. In particular, and I won't go through the details here, but as we review in our paper, what you can do is you can rigorously map, at least to some level of accuracy in your calculation, what we're doing here of calculating the spectrum to these fragmentation functions. So if I imagine that the initial hard process is the dark matter decays to some XX bar, for example, this could be nu bar, but it really could be two arbitrary states in the standard model, then what I need to do is calculate the fragmentation function for X evolving into some state of interest. S could be a photon or a neutrino, for example, and also X bar, combine the two, and that's the full spectrum. Now, of course, it could be the case that the dark matter decay could be more complicated. You could have some 3-body, 4-body, or n-body decay. There's actually also an associated expression for that there. I just haven't written this. And so in this talk, I'll focus on the simple case of 2-body decays. But actually in our public results, we give all the ingredients necessary that if you have some arbitrarily complicated hard process, you can also use our results to get out the spectra that your model would predict. So at the moment, we've just restated the problem. We had to calculate some dark matter spectra. We now have to calculate some fragmentation functions. But what's nice about this is that we can draw on the vast literature of fragmentation functions and use a number of tricks that are known for computing them. In particular, and I'll describe this in a bit more detail later on, there's sort of a gluing function that is known for fragmentation functions. So if instead of just evolving these objects all the way from the high scale down to the low scale, I can evolve them through some intermediate steps and then just glue those pieces together to get the full result that I need. And so we'll take advantage of this to break the calculation into 3 steps. In the first of these steps, what we're going to do is we want to evolve all the way from the dark matter scale down to just above the electroweak scale. We will do this using the DGLAP equations, but we won't just use pure QCD DGLAP. We'll use DGLAP with all the interactions in the standard model, including all the relevant electroweak interactions. At this stage, we'll then match onto the unbroken standard model. So essentially, we'll integrate out the various electroweak scale particles. And actually, this is the point where we'll count for electroweak masses, which we would have neglected in stage 1 of the calculation. Finally, rather than matching onto, say, some experimentally measured fragmentation function, we'll match onto Pythia, which we really do I think is capturing most of the relevant physics below the electroweak scale. And this will allow us to get arbitrary final states that we're interested in, photons, neutrinos, positrons, antiprotons, etc. So what I want to do for the rest of the talk is just give a little bit of insight into the steps, primarily focusing on one where most of the meat was here. But also just let me mention at this stage that there's a clear assumption that we've put into this. So we're imagining that between the dark matter scale and the electroweak scale, no other relevant threshold was crossed. You could imagine, for example, if you think at high enough energies that say supersymmetry became relevant, well, that should be broken potentially somewhere between the dark matter scale and the electroweak scale. If that was the case, you would need to modify our calculation by introducing some other matching scale in between, but we haven't done that here. So let me just run you quickly through sort of the overview of the logic. I'm being a bit simplistic in my discussion of what happened at step 1, but please press me if you'd like to know more details. So the idea is that we start our evolution at the high scale where the dark matter mass is. And so to begin with, we can imagine what is asking the question of what is the fragmentation function before any evolution has occurred. So in the particular case of dark matter decaying to 2 neutrinos, well, we'll just have a delta function, which was our naive expectation for the spectrum, where so all of the energy fraction of the neutrinos is sitting at 1, and then there can't be any change in species at this point. So there's just a Kronecker delta associated with that. What I want to do is then evolve this down. And the way that you can do this at the level of accuracy we're working is using the DGLAP equations. So just to remind you, if you haven't thought about the DGLAP equations for a while, what these are doing is they're saying that as I move through virtuality, how can the energy that was initially just in these 2 neutrinos be repartitioned around amongst the various states? And what the DGLAP equations say is that there's 2 ways that that energy could be reorganized. Let's say that I'm thinking about the DGLAP equation at some given energy fraction. Well, one contribution I can have as I evolve is that a particle with a higher energy fraction could split, and then it comes down to a lower energy fraction because it's undergone some real emission. And so that's what's happening in this first term here. We integrate over all fragmentation functions with high energy fractions, weighted by the splitting functions, which account for how that splitting could occur. One way, however, you could lose something from your fragmentation function here is if you had some state and it had any splitting at all, well, then it's going to have fallen out. And so that's the second correction here. And because the probability for any splitting at all by unitarity is linked to the virtual corrections, these are often called the real and virtual contributions to the DGLAP equation. But it's a pretty simple picture for what the evolution is actually doing. So this is, as I said, this is a bit of an overly simplistic view of what we're doing. Let me just give you a bit of a taste for what's actually happening under the hood. So in truth, I've suppressed the flavor indices here. And when we're working in the full unbroken standard model, in total, when you account for those flavor indices, we're going to have 2,204 coupled fragmentation functions. So you need to do some tricks to try and reduce the number of equations that are coupled together. And people have thought about this. And actually, indeed, what we do in our work is rely on results that have been developed earlier, in particular by my collaborators, Christian and Brian, and also a student, Davide Provasoli. So in these works here, what they were doing was that they were calculating the fragmentation functions, including the full unbroken standard model, but their motivation was thinking about what you would see at 100 TeV collider, where we actually know that a lot of the same electroweak effects that are relevant for this heavy dark matter will also be relevant for the observations there. Actually, we teamed up because I realized that these same observations they were using for the 100 TeV collider could be pushed even further and applied to the type of dark matter I'm interested in here. So it's not just the flavor indices that are going on here. There's a lot of other interesting physics. So, I mean, famously, the electroweak sector will generate double logs because there's incomplete cancellation between the real and virtual contributions. And then furthermore, due to the chiral nature of the electroweak interaction, you can actually generate polarization through the evolution. And this was a point that was first noticed in this paper by Anish and Valter. So the point here is that even if you started at the high scale with some unpolarized state, the chiral nature of the electroweak interaction will polarize that by the time you get to the electroweak scale. So just to give you a very clear example of this, let's imagine that you started with a left-handed or a right-handed electron at the Planck scale, and then you evolve that down to the electroweak scale. The spectrum of electrons, so left-handed plus right-handed, you get at the low scale is very different between the two. In particular, you can see that the left-handed one has more soft particles, and this makes sense because the left-handed electron can undergo more interactions, so it is more likely to have an emission. And so this effect is something we need to keep track of, and we do. But then of course, what we do is we carefully solve the DGLAP equations. But pictorially, what you can think about what is happening is that the DGLAP equations really give you semi-classical evolution. Everything is being controlled by those splitting functions. And so you can sort of imagine that what happens is you have some splitting, and then there's some probability of no emissions. Then you can have another splitting, another splitting, another splitting. And then also these particles that come off can split, and critically will include the various interactions that P3 is missing. Eventually, you can produce colored states, even if you didn't start with them. They can produce gluons. And then at the end of the day, even if you started with neutrinos, you can end up with a situation where you have essentially every particle in the standard model, which is sort of, I'm just showing you a subset here, but you'll get some distribution of these ultimately. So this is what you would get by just doing this DGLAP evolution. What I want to tell you about now is one other feature that we realized is important, but we do not have a full accounting for. And this is this issue of soft coherence that gave you the yellow caution I showed you right at the outset. And so in order to understand this sort of at a cartoon level, let me draw your attention to this particular gluon here that's been emitted by this down quark. The effect of soft coherence is going to be relevant in the limit where this gluon has very low energy fraction, or so it's a very soft gluon. So the DGLAP equations account for collinear and soft collinear splittings, both of which are enhanced, but it does not account for purely soft splittings. For purely soft splittings, famously, the amplitude will obey a factorization expression where you can take the amplitude for emitting this soft particle and relate it to the amplitude without that soft particle, and they're just connected by this famous iconal factor, which is written in terms of the momentums and polarizations as written here. But what's interesting about this is because the factorization happens at the level of the amplitude, to actually figure out what would happen to the observable, you need to look at all the places this soft gluon could have been emitted, add them all together, and then take the mod square. So you can get some genuine quantum interference, which will break this semi-classical picture of the showering that I showed you earlier. You could ask, would you expect this interference to be generally destructive, constructive, or is it just going to be a mix of both? Actually, it turns out you would generally expect the interference to be destructive. And the reason for this is if I draw your attention again to this gluon, in the limit where it's very soft is very long wavelength. And so it won't just see the down quark, it will now eventually resolve the anti-up. And in fact, it won't be able to distinguish the two. So it will see both of their color. And because they came from an uncolored W, it will see zero color. So if the quark can only, if the gluon, sorry, can only resolve zero color, it never should have been emitted. And so this is why we would generally expect destructive interference. So this is Many of you may have heard of this. This is the famous color coherence effect in QCD, or it's also related to angular ordering, because if this gluon was emitted within the cone at the down in the anti-up, well, then it wouldn't see both of them even in the long wavelength limit. But again, this is hand wavy. What you actually have to do is do the calculation for the interference between the various places the gluon could be emitted. And then you can also see that this destructive interference emerges. So in the QCD literature, this is very well known, but this is just some detail associated with gauge theories. This same effect should be happening also in the electroweak sector as well, although this has not yet been worked out in detail. So because of this, we can't just immediately, without doing a number of calculations, work this effect into our result. But what we did notice is that going back to the QCD result, which, as I said, has been known about for a while, this is a review article from the 80s, they pointed out the full expression for what this soft coherence does to the real radiation. So essentially the soft physics here. How does it suppress these emissions? Like, what is the expression associated with those suppressed emissions?
Nick, may I interrupt you just again to follow? When you are putting this production as going through W and Z, whatever, is it possible to view it in such a way that it is like W boson decay boosted into different frame, or your W bosons are just symbolic?
No, good. So actually, when I come to the second step and I need to integrate these out, if I'm evolving over some tiny little scale, I can actually map the fragmentation functions literally to the W decay, which is what you're saying here. Okay. But what I really should think about,
right. But then, okay, if it would be like this type of factorization, then I would say, aha, let's measure W decay in the lab, and then just boost this distribution into whatever energy you are considering, right?
That's not good. So, but this is not exactly what's happening here, right? This is
no. That's why I'm asking. That if it would be just W decay, but only in a different frame, right? In where W not in the rest, but W kind of fast moving, right? Then it would be very simple. You can just boost your W decay distribution into in whatever frame, right? But if but then if it's not the case, then it's not it's not just exchange of real W, then it's just virtual W, and then it's very different, right?
It's not, but I mean, just like, for example, to understand what you're saying, if you would think, I could measure the neutrino fragmentation function, maybe I could just boost this arbitrarily far, and that would give me what the spectrum is. But as I evolve in energy, new effects become relevant. For instance, like, we can't do a low energy measurement and extract the full associated thing when I'm operating in a regime where the full unbroken standard model is relevant. Like I can get copious W and Z emissions because essentially their masses are irrelevant if I'm operating on an EEV scale. There's no low energy measurement I can do that would extract that physics that I could then boost to higher scales. So I really do need to think about calculating this a priori. There's not some immediate measurement I can do.
But look, what I'm trying to ask is kind of simple. Whether your W are kind of on the mass shell or it's a virtual W. That's it.
Good. Excellent. Okay, now in this process, you should imagine these as all virtual.
Yeah. You see. So then it's just the interaction of neutrino with other light particle, and mentioned W is not that crucial, right? I mean.
Good. Yeah, that's right. But I mean, maybe I'm not fully digesting your point. But when we come to the next stage, it will actually, I can think about it as sort of an on-shell W. But yeah, generally you should think about these in these showers as these as virtual particles. Yeah.
Yeah. Okay.
Yeah. Good. Thanks for the clarification. Good. So I was in the middle of this long-winded.
For this color coherence effect, well, shouldn't I expect naively it's a small perturbation to my energy spectrum, but maybe some larger perturbation in number spectrum? That's why you focus on it so much. Otherwise, it's a small. The correction is lambda QCD, right? It's in the lab frame, and it's not going to be important.
I will show you what it does to the spectrum in a moment, and you're exactly right. Yeah, you're exactly right.
Oh, okay. So it's safe. Okay.
Good. You're exactly right. You will see what happens. It's a tiny perturbation in energy. It's an enormous perturbation in number, right? So this is anyway. So what we've done at the moment is we've taken the known, just to go back to like the story of how we incorporated this effect, the known QCD result, and we noticed a cute thing, which is that you can actually see this as coming out of a deglap equation if you do a change of variables. And so in our paper, we derive what that change of variables is. And so this means you can do the deglap evolution using the semi-classical picture, change variables at the end, and you get the dominant effect of soft coherence. But it's not perfect because this only accounts for the real radiation. If you suppress the probability of emission, you've enhanced the probability of no emission and therefore also the virtual effects, and we don't correctly account for that. And so what this means is we'll actually ruin our momentum sums, but only at a small level of about 5%, which is consistent with what Jen was suggesting, that this doesn't change the energy distribution that much. Okay, so in this sense, our result will have an irreducible error associated with that, and this is something we would like to improve. But let's just see what this does. You lop these particles off, and you can see going back and forth, it generally just suppresses the distribution of all the states at lower energies, because even if I'm cutting off some gluons here, this gluon then could have become quarks, et cetera, or other states. And so the production for any of these soft particles will be eventually reduced. So you can see that this can create quite a large difference, which is why we wanted to have some incorporation of it. But we know that we've got a bit of an ad hoc treatment here that we'd like to improve on. Good, so now we come to the second step, and then what I'm going to imagine is that suddenly these electroweak states become massive and we need to integrate them out of the spectrum. And so we can essentially now treat them as on shell and get rid of them using the second step I mentioned earlier. So just to quickly flag, for time I won't go into too much detail here, but the point is that fragmentation functions obey a gluing property. Essentially, you can calculate evolution from A to B and from B to C, and then you can glue these together using this formula to get the evolution from A to C. And that's what we're going to take advantage of. We just evolved from the dark matter scale to just above the electroweak scale. I'm now just going to evolve over an infinitesimal scale through the electroweak scale. And the reason it's infinitesimal is I don't want to generate any large logs here, which we were carefully resumming in the first step. So this is a pretty trivial calculation. You just need to calculate the tree level, the level of accuracy we're working, the just tree level decay of these particles. The one thing that makes it just a little bit fiddly is, remember I said that you can, no matter what you do, you're going to generate polarization. And so therefore you need to account for the fact that, for example, the left and right-handed tops will decay differently. And so you need to account for that carefully and get the different decay spectra out of these. And for instance, when we were doing this, it's a fiddly enough calculation that, for example, in one of the canonical references that had calculated this, we found that they had an error in their interference term here. So you can either have a transverse or a longitudinal W here, there's interference between the two, and there was an error in the sign. So it's a slightly fiddly calculation, but intuitively it's pretty straightforward. You're just doing some tree level Feynman diagram to calculate this fragmentation. So what we do here is you then, to actually do this gluing, pictorially, you can imagine what's happening is we're just getting rid of these W's and the Higgs, for example, and then this will produce more other particles like neutrinos, B quarks, photons, for example. That's what's happening through this threshold. Then we'll do this gluing one more time, and what we'll glue that result onto is a result where we've evolved from the electroweak scale down to some infrared scale, essentially, which is what we're showing at the end. I'm showing you on the right-hand side here. And generally here, we pretty much trust Pythia. There's a couple of caveats we discussed in our paper that we look to improve, but on the whole, you should think that really what we're doing is just running Pythia here down to the low scale. And so then the sum result of our full evolution is we started out in virtuality at a high virtuality scale of just this delta function. But then by the time we've evolved down to the infrared scale, you can see that we've generated a very complex distribution of all the different types of particles you might hope to search for in indirect detection. So earlier on, I just showed you the neutrino and the photon spectrum. But of course, there are others, and here I'm showing you them in detail in this plot. So that's just a quick overview of how we did the calculation. Of course, there's a lot of details I haven't gone through in full, but hopefully you get an impression for what we did to calculate this. And what I want to show you now is some results using this formalism. And in particular, as advertised, I want to show you some spectra at the Planck scale, just because I think that's pretty cool. To begin with, let me just show you our results as compared to some other references. So actually, for most states, we get very good agreement between Pythia and other things that have been produced, like PPPC. Of course, this shouldn't be too surprising. If I'm at low masses, I haven't added much to Pythia. Eventually, I'm matching onto Pythia. So if not too much is happening, and for example, what Pythia is doing is largely in, for example, hadronic states is really just QCD deglap, which is well understood, then I should expect to agree, and we do. But in some channels, we don't agree as well. In particular, it's the electroweak dominated channels, and notably the neutrinos. So that's what I'm showing you here. So in particular, for quite a low mass from our perspective of about a TeV, if I look at the neutrino spectrum from an initial neutrino state and the photon spectrum on the right, I'm showing you our results in orange, the results from Pythia in the dashed curve, and the results from PPPC in the dotted curve. To remind you, PPPC was Pythia with none of Pythia's electroweak corrections turned on, but with their own version of the electroweak corrections turned on. So actually, you can see that there are a number of differences between these. I think that our results are certainly more accurate than Pythia here because they're missing a number of the important electroweak corrections. But the difference between our results and PPPC is a bit harder to explain. I mean, so for example, just to draw your attention to the fact that we have hard photons, but Pythia doesn't, is coming from the fact that our Ws can emit photons, whereas Pythia's can't. But the difference between our results and PPPC is a bit harder to determine. I don't think that everything PPPC did at these lower masses is fully accurate, but I know that we're missing effects. For example, we only include the electroweak boson masses right at that second stage. It would be nice, for example, to actually match our results onto some fixed order calculation to try and improve that. So I think at the moment, for some channels, the differences between our curves and PPPC at lower masses is sort of the theoretical uncertainty that we would like to improve.
Hi, Nick. Beyond the low mass spectral behavior, a critical component is what's the dollar function part, right? Here in your spectrum on the left panel, it seems like you lose most of your neutrino energy and flux. I assume they are lost into electrons or muons through the weak emission. Is that the case? And
yeah, sharp eye, nothing. I didn't explain that in detail. You're referring to this here, right? Can you see?
Yeah, this is super crucial, right? Because your spectra, energy got softened hugely. You lost your initial flux. Can you elaborate on that?
Yeah, good. No, yeah, nothing. I didn't sneak by there. So what has happened here? Actually, it's really not a difference. It's a plotting difference in reality. So, for example, for PPPC, they didn't have like enough X bins at the top to actually resolve what should happen here. Because in truth, there's then a delta function at X equals 1. And then, of course, the continuum doesn't just smoothly merge into the delta function. It actually has to turn off. And actually, the turn off is controlled by the W and Z boson mass. Because to actually have anything other than a delta function, you must emit one of those. And so they will carry off some of the energy. And so you'll have a slight separation between the two. In our results, because we did the calculation, I can control everything. I made sure that we had resolution to sort of start to see that effect. But in the other results we had here, and when I ran Pythia, for example, I didn't keep that level of resolution. So this is more of a plotting feature that I potentially could have washed away, but you're exactly right. And to emphasize,
so you still have a sharp peak like at 1, but you just have a gap at where maybe the X equals 1 minus MW over M dark matter.
Exactly. And to emphasize with our results, the way that would come in is that there's some coefficient of a delta function. And in our public code, you can extract, we give you that coefficient of a delta function as a function of mass. So you can get that out as well. Yeah, it's in our results.
Okay, but I have another question, but maybe you can comment at the end of your talk. This finite mass effect and putting into those, calculations have a lot of scheme dependence in some sense, right? People struggle in which scheme is the correct way to take those finite mass effects. It sounds like you are pretty confident with your own calculation, but it would be nice if you comment on are there any subtleties around that.
Yeah, maybe in the interest of time, maybe ask me that again at the end, but I can say a few words on that. Yeah.
Okay.
Good questions. So then what I want to do is let's just start raising the mass here, because I guess getting towards this point, it's at higher masses that I trust our result, because then the approximation that the W and Z are massless becomes better and better. So if I go up 3 orders of magnitude to a PV mass dark matter, I've just shot past the end of the PPPC table, so I can't plot that anymore. And you can see that Pythia and our results are broadly still in somewhat agreement. I mean, this is a log plot. There's quite large differences. Up to some facts where, the missing triple gauge couplings means that Pythia just can't predict hard photons in this process, whereas if you include the full electroweak interactions, we can. That's what's describing the difference on the right-hand plot here.
I'm sorry to ask to be there, but look, when you are discussing this decay to neutrino, does your result for the spectrum depends on detail how decays proceed? No, for example, chi, it could be decay to W boson and then the neutrino, or whatever, or it doesn't matter for you.
Oh, it definitely, the initial state does matter. In fact, I'll show you in a slide, like the spectrum you get out will definitely depend upon the initial state. And in our public results, we take we have the formalism there that no matter what your initial decay,
not dependence on the initial state. Of course, it does depend on the initial state, but then the details how the decay proceeds. I mean, they decay, for example, to W boson first, and then to neutrino, or you see that in this way it could be something kind of dynamics of the decay itself. Does it imply that it's just a vertex? Chi goes to neutrino without any details, right? Or what?
Yeah, good. This is, and like you could imagine also you could calculate higher order corrections to that, the initial.
Yeah, right.
Yeah, at the level at which we're accurate, we're calculating, those are irrelevant. Like at higher order, you would need to think about, and you also then need to be careful you don't double count them in the showering, right? It's a similar issue appears in Pythia, right? If you're doing higher order, matrix element calculations, you need to think carefully about not double counting things in.
Yeah. Okay. So
at the level we're operating, this is some future,
Thanks.
Yeah, fair question. Thanks. So good. And then, so Pythia is keeping up, but eventually what's going to happen is if I go to high enough masses, Pythia just can't produce a large enough electroweak shower. Like it's these triple gauge couplings that allow that shower to develop. And so if I go up another 3 orders of magnitude in mass, Pythia has just lost it. It's just fallen way behind what we had, and it no longer is predicting anywhere near as much information as what is in our result. And this is what I showed you at the outset. So as I said, the difference.
So Nick, so this hard photon spectra is generated by, I split into W, and the W radiate the photon, right? That's a major source of the.
That's my intuition. Yes.
Yeah. Do you know since you keep on mentioning triple gauge boson couplings, right? Do you know what's the impact on the W and the Z the spectra? Before your last stage of matching, is it? I'm wondering if it's just a matter of fact, because formally it's a higher order compared to your leading interactions, right? Where neutrino interact with W and Z directly.
Yeah, so I mean, of course, the spectrum again will be different because all Pythia has is like single W or single Z emission off fermions. That's what it includes. I mean, our formalism could, of course, give that to you. I don't remember what that looks like off the top of my head. At some stage when we calculated this, I would have looked at those plots, but I don't remember off the top of my head. I mean, intuitively, the spectrum is going to be quite different. Like you will also have more soft W's and Z's because of the splitting that they can undergo, for instance. But I can't give you more than that sort of qualitative answer at this stage.
Thanks.
No, thanks for the question. So to emphasize again, what I was saying was that I expect the greatest difference as to what exists in the literature right now to be in the electroweak sector, because that's where we've made the biggest changes or improvements. But if I look at a hadronic state, just to emphasize this, there will be differences, but generally there's qualitative agreement. So if you recall, I mentioned these authors who've been thinking about extremely heavy dark matter, like say a gut scale mass dark matter, decaying to some QCD state and then looking at its evolution using the QCD DGLAP equations. And we find that our results are qualitatively in agreement with what they have. But again, there are differences. So for instance, again, they're underestimating the emission of the hardest photons because they don't have any of the electroweak processes in their evolution at all. But there's much better agreement here, even at a higher mass, than there was between Pythia and the neutrino spectrum. Okay, so then as advertised, I just wanted to show you some spectra going all the way to the Planck scale. So here I'm just choosing, really there's an enormous number of possibilities here. Our formalism, we calculate all the possible fragmentation functions for every state in the standard model and all stable final states up to a proton. We don't consider anti-helium, for example, at this stage, although that would be an interesting thing to consider. And so I can just take any of these. I've just taken 4 of them, for example. You can see what the decay is in the bottom right. And then I'm going to show you initially the mass, a dark matter mass at a TeV. And then I'm going to show you one mass for every decade all the way to the Planck scale. And you can see that depending upon exactly what this process is, the evolution can be quite different. So in the bottom left here, you can see that there's just more and more muon neutrinos being produced, but the evolution is not always so simple. For example, for the photon spectrum, you can see that there's sort of a reduction in emission at intermediate energy fractions, but an increase at lower and higher. And then you really need to dig into exactly what's happening for the different emission processes to understand how all these can occur. One aspect, though, that I think is quite interesting about this is that you can see sort of a more generic feature is that as I go to higher and higher masses, the evolution is slowing. This is, the rate at which it's slowing depends upon the channel, but you can see that generically it is slowing down. Like the difference between a Planck mass and 1 order of magnitude below that is not anywhere near as great as going from a TeV to 10 TeV. And actually the reason for this is that there's sort of a nice parallel in some senses between properties of the DGLAP equations and properties of the diffusion equation. And sort of what you can think about as happening is that ultimately, as I just what the DGLAP equations are doing is they're repartitioning the momentum or the energy between the various products that could exist in the standard model. And eventually, as these become more and more partitioned, there's sort of a well-mixed state that you're approaching. And so this is why the evolution is slowing down in some senses, which I thought was quite nice. Of course, to advertise, by the time I get to the Planck scale, some of the logs that the single logs I'm missing are going to introduce, order 1 theoretical uncertainties. But nicely, they're order 1. You can check that the single logs never get larger than 1, even by the Planck scale, which means that our failure to include them and resum them isn't going to lead to some orders of magnitude uncertainty. So I don't think that even the Planck scale spectra I'm showing you here are necessarily totally nonsense, although they will have larger uncertainties than, say, the TeV scale spectrum.
But Nick, can I just ask you about this Planck scale? I mean, what's the model for a Planck scale dark matter? How do you produce it in the early universe? I mean, is there anything?
Good. Yeah. So, I mean, so that answer I don't have immediately offhand. I know that people have talked about, what is the mass scale that these WIMP-zillas go up to? I don't remember that off the top of my head.
That was like, I think 10 to the 11 GeV, if I remember.
10 to the 11 GeV. So there's,
I mean, it all depends. It'll all depend on the couplings, right? I mean, there's, if there is some coupling and you have, sort of a high reheating temperature, you can eventually, I'm sure you can cook something up that would do it. I think what's probably more difficult is making sure that the lifetime of such a thing is, age of the universe or longer, right? That's where I think it's going to be. That's probably harder than actually getting enough of them present to make up the dark matter density.
Yeah, but don't you also, Keith, if you go above the gut scale, you will produce monopoles, I mean, all sorts of stuff.
I'm not saying that you reheat necessarily above the gut scale.
Oh, I see.
Yeah, I mean, the whole thing with monopoles is a little bit tricky anyway, but because, are they fundamental particles that you would, pair produce? But putting aside that question, no, you don't have to go. You can produce particles that are heavier than the temperature. So I mean, there's all sorts of ways of doing that.
Yeah, but you're right. The lifetime is important. Yeah, I mean that's also right.
Yeah, I mean, typically a Planck scale particle
exactly.
doesn't live very long, right? That's
right.
That's where you.
Could it be some like kind of mini black holes? This of Planck scale, or they are not relevant to this? I mean, they are also dark, right? Because they are black.
I think primordial black holes of this. I think they're ruled out, or
ruled out.
Right.
That's what I think. That's what I thought, but I'm not sure. Yeah.
Yeah.
I think for primordial black holes, they have to be much, much larger, if I remember. Solar masses.
Yeah.
Again, that's I think a lifetime thing.
Yeah.
So in the sense that this Planck black holes would decay soon.
Yeah.
I see.
Yeah, it's a totally fair point, Tony, and I think something to keep in the back of your mind that not every curve here is equally well motivated, but from the point of view of how we do the calculations, this mass scale is sort of just like an initial condition you put into like these equations we're solving. So there's no reason we can't just crank it up, which is what we did. But yeah, I certainly appreciate, and also from the experimental point of view, it's probably going to be well below the Planck scale where it's easiest. These results have the most use. Yeah,
no, it's fine. Yeah, no, I understand your motivation for pushing it up to some natural scale there. Yeah, I was just curious. No, it's all fine.
Good question. No, Keith had some interesting points there. Good. So with that, let me wrap things up. And as has been alluded to, especially through a lot of the great questions that have happened today, there's a lot going on in this story, like exactly how much dark matter is out there. How would you ever hope to distinguish a signal from potential backgrounds, etc.? There's a lot of challenging aspects to this. But one important aspect is producing these spectra that you would get out of the decay. And as I've shown you here, I mean, these are a critical ingredient for the signal prediction, and what the experiments are using at the moment, we know can be orders of magnitude incorrect. So we've made our full results that I showed you today available at this GitHub here. If you're interested in this, please have a play around. And if you have any issues, reach out, but we tried to make it as easy to use as possible. And already we've actually working with the IceCube collaboration to swap over from the Pythia results to our results. Another thing I emphasize to you though, is that although we know our results are an improvement, there's a couple of places where we know we would like to do better. And so I think there's a few clear targets for improving these results going forward. And I've already mentioned this, so I won't say that again. Okay, thanks a lot for your attention and thanks for the great questions. I'll be happy to take any more if there are.
All right, thanks, Nick. Do we have more questions?
So regarding the earlier question about the lifetime, Nick, I think for your purpose, you don't need a dark matter decay. You can just analyze a pair of dark matter to the given final state, because your calculation is just for an highly energetic standard model particle goes through that electric showers, right?
I mean, yeah, from the perspective of our spectrum, that's correct. But the reason we framed all of this in terms of decay is because of the Kamiakowski grease bound, right? So there's eventually, normally people don't talk about annihilation at these very heavy masses because you need to do something special to explain how it was produced, for example. It's not going to be just generic thermal dark matter. So, but I mean, people have written down models where you can have very heavy dark matter annihilating. You have some interesting cosmology, and then our results just port over. You just need to put a factor of 2 into the mass or the energy scale associated with our spectra. And in fact, when you download the code, we just have a keyword. You can say decay or annihilation, and it'll swap that around for you.
Yeah. So basically, you are comparing to either a decaying dark matter's lifetime problem or comparing to the annihilation for heavy dark matters. Right? So you choose in your paper choose to use the decay of dark matter as an example.
I mean, in principle, because it really doesn't matter, because this spectrum, I mean, if you go and look at what the rigorous definition is, you normalize out the Born cross-section or the Born lifetime. So, the overall scale of these things is factorized into a part of this that we're not even talking about. We're just looking to do the field theory calculation of how, what is the distribution of particles from this process. That's really the only thing we're looking at in our work. And that's an ingredient that then goes together with all the other things that were mentioned.
So I had a question. So basically the same topic as before. So if I look at your curves compared to Pythia curves, most of the effect is in the tail. So how much of the constraints on dark matter annihilation or decay to nu bar comes from the tail of the distribution? Do you have a feel for that? Or basically the question is, how much do the bounds change?
So for that, actually, so this was a point that was partially explored in this paper here. So I would refer to this if you'd like to see more details, but let's just say the EEV case, right? So we know that IceCube is seeing neutrinos up to order a PeV. The reason I focus on the neutrino case is the photons, you need to think about the propagation effects, which is another story. So let me not mention that here. But if you're thinking about the neutrino case, they've seen up to a PeV. So that's 3 orders of magnitude down from the mass. And so it's really going to be this regime around here where their limits are coming from. And you can see that we have, at least an order of magnitude more flux than they do here. And so you would predict at least an order of magnitude stronger limit, right? But this is something that they will update going forward.
But I guess the limits where the dark matter mass or, well, in the case of annihilation, also the mass, when that mass is in their range of energy sensitivity,
I would
expect
less than an order of magnitude difference. Yeah, absolutely. Yeah.
Okay, thank you.
So you mentioned that the energy in the intermediate scale or the low energy scale, the prediction or the calculation is not so reliable. So do you have any analytic way to estimate how much of whether that's an overestimate or underestimate? And do you have a feeling of how you can improve the prediction?
Good, you're referring to these plots here, for example, Raymond.
I was thinking about the EEV plot that you were showing. You were saying in the final plot that you were showing. I thought you were saying that in the this one in the intermediate scale right here, and then the low energy scale, you may not trust your calculation.
Yeah, good. Yes. And this is because this goes back to this soft coherence point. So what we've done at the moment is good. And I can give you, yeah, we do have a way of estimating this. And this is, I mean, in more detail in our paper, but let me just give you like what we did. So this is just the result for QCD for what you get for the soft radiation when you, the low energy fraction radiation when you include the soft coherence effect. This was something that had been calculated and appeared in this review article. And so what we noticed is that you can just do some substitution to get this result out of a DGLAP equation, which is what we're doing. And so you can do this substitution to our results to essentially improve the soft coherence, to add that into the real radiation. But we know that's not the full story. As I said, that's not including the virtual corrections. And it's a pretty ad hoc way of doing it. To really include the virtual corrections, you need to think again about how to modify more details of the calculation. I can say more about that if there's interest about ways we're thinking about doing this. But we can estimate the error as follows. So actually, Pythia already has some degree of soft coherence in there. It's actually not naturally in there because Pythia is a PT ordered shower, not an angular ordered shower. But because soft coherence is a real part of QCD, they have to include it somehow when they tune to fit known distributions. So Pythia is including soft coherence. So then the question is, when we do this correction, should we do it to our full results? If we do that, we're certainly overestimating the size of soft coherence because we're double counting it at the low scale. Or should we just do this trick to the high scale before we glue it with the other things? Or do we not do it at all? This can give us some range of results. So what we did in our paper is we just did it at the high scale, and that's the orange. If we didn't do it at all, we know that's an underestimate. That's what's in blue. And if we do it to everything, we're definitely double counting. That's in purple. So what you can see is that lower energy fractions, the difference between these is getting larger and larger. But actually, if we go to, if we look at the same plot where we go to very, very high energies, essentially this effect has been reduced because this physics is being pushed to lower and lower energy fractions. Like where this is relevant is being pushed off the plot where we already know we have errors that are orders of magnitude that we don't have under control anyway. So this is again, it's not like a rigorous accounting of the errors, but it gives us some idea that, you know, intermediate energy fractions, the size of the error is maybe, you know, order 1, but it's not enormous. So this is where we would like to do better.
I see. All right, thank you.
Any other questions? How would one validate this calculation? So what kind of data do you need?
Oh, I mean, in pretty good. Okay, good. No. Okay, no. I don't need to be too facetious. Yeah, obviously you want a PeV collider, but what will validate a lot of this physics is a TeV collider, a 100 TeV collider, because the electroweak sector, the importance of it grows dramatically between 10 TeV and 100 TeV. And actually, a lot of the formalism that we are sort of building on in our work here was all developed knowing that this is going to be important at 100 TeV collider. Like I had these references here. For example, there's many more, but these works here have shown that electroweak effects can change, you know, a number of observables by order 1 level compared to not including them at 100 TeV collider. And just to give you sort of one manifestation of this, actually a number of, I mean, I can't remember a quantitative answer to this, but this was just a cute fact that a number of neutrinos will actually be detected at 100 TeV collider because they'll produce jets from the emission of a W and a Z. And that's a pretty dramatic departure from how we normally think about neutrinos. And so a lot of the formalism that this work is built upon will be cross-checked carefully by, you know, at 100 TeV collider. And if things are matching up nicely, I'd have confidence, you know, unless you then between 100 TeV and your dark matter scale, you cross some other threshold, maybe like a SUSY breaking threshold or something else, I would have confidence that our results are accurate.
Interesting. So any hope that neutrino cross sections can help you here? So like DIS at, you know, the super highest energies that IceCube measures. I guess the center of mass is still too low.
Another place measurements could improve, like you might worry that some aspect of Pythia isn't capturing all the relevant physics we care about. And one way of cross-checking that is that instead of matching onto Pythia, we could match onto some fragmentation function, which could be got at by the type of measurements you're suggesting. And this is something we're interested in thinking about also, is doing comparisons to Pythia, because Pythia is tuned to operate at specific scales, and it's certainly not designed with what we have in mind here. So it would be nice to just check that experimental measurements of fragmentation functions don't give crazily different results to what we're suggesting here. But then you really need to go case by case. The thing that's really nice about Pythia is it's just all purpose. So we get everything at once. We don't need a different fragmentation function for a B quark and a different fragmentation function for all the other states we're considering, for instance.
But existing data, you know, kind of, you know, you still have this cosmic ray data, whatever. I mean, can you use this data to, you know, to verify or to see deviation, or I don't know how, what is the status of this?
Yeah, so good. So what I guess what you have in mind here is that, so some of the highest energy particles we've ever detected are these cosmic rays. They hit the atmosphere and they actually produce the type of shower that I'm talking about here. So that is in principle. So actually one aspect of the evolution that is quite different here is that the atmosphere changes the evolution of these states quite dramatically. So that you would need to disentangle that. But in principle, if you could, or you could redo our calculation for an in-medium effect, you may be able to do some cross-check from that. But it just, of course, it's never going to be as clean as anything you can do in a collider, but maybe you could get some insight for that. I haven't thought about it in a ton of detail, but it's a good suggestion.
Okay, thank you.
No, thanks for the suggestion.
Yeah, some people are discussing, well, maybe this wouldn't work too, but high energy neutrino scattering on the atmosphere of the sun and then detecting the shower that comes out of that on Earth. Maybe this is a type of, but I don't know how large the energies that they can go to are in that kind of measurement.
Yeah, and I guess
because you wouldn't necessarily have a thick atmosphere in that case. Maybe the atmosphere of the Earth would also skew the measurements too much. But
yeah, I mean, one way of maybe spinning some of these suggestions, right? Instead of necessarily, of course, you know, there could be some experimental insight into how to get these out, but one thing I'm not that aware of, but would be interesting to consider is that any of these calculations, like actually how the shower develops in the atmosphere, or alternatively how this skimming could occur in the sun's atmosphere, at sufficiently high energies, the same physics I'm talking about today must enter somewhere, right? And so I wonder if you could take those calculations, I would be surprised if they're using all of this physics, because a lot of this electroweak physics has really only been developed in the last few years. What they could do is they could incorporate that physics into their predictions. And it would be interesting to see whether, you know, particularly in the air shower case, whether that improved agreement with what we're seeing. And if it didn't, that would give confidence. If it didn't, I mean, we definitely believe in the standard model at some level. So these authors are very careful calculators, but there'll probably be some other physics that we're missing. But that's one way of, you know, sort of incorporating or bringing these stories together.
interesting. Any more questions?
So Nick, I asked them, I think it should be postponed to the end of your talk, which is how do you exactly do the matching in the grain step? Because when you do the splitting calculation, both gauge bosons are massless, right? Do you evolve the evolution up to around the scale of the W and Z mass? Then every massless gauge boson suddenly become massive, and with your, you know, just by injecting extra components in their energy, and then let them decay and then pass it to PCI. And does it have a name of your scheme? And are there other schemes of this matching?
Yeah, good. No, so eventually the types of details you're suggesting are relevant, like exactly what the mass is. It's a high enough order of the calculation becomes scheme dependent. But actually the beauty of what we're doing here, like what makes it life a lot easier in this step is by doing this gluing process, all I need to do is calculate the fragmentation function for evolution of, I'm now working in the broken standard model essentially, if like a massive W just above the electroweak scale to just below. So actually all I need to do is decay it. And at the level we're operating, it's just a tree level decay is sufficiently accurate. Like the 10% improvements you might get by working at one loop, we've got 10% errors everywhere. So we're not worried about
yeah, sure. I mean, I understand the decay part, but you know, I'm asking about from massless to massive step, right? That's from top to down, not from the grain to the next PCI step, right?
Good. So yeah. At the level we're working at the moment, we don't incorporate that sort of thinking at all. Like in step one, everything's massless. Step two, masses appear and they're gone immediately. Now, this is why I think if you go to high enough energies, this is probably going to be fine. But especially like this treatment is why I would not trust our results to be absolutely correct at, say, the TeV scale. Now, how you would need to improve upon this is I'd want to take our calculations and match them onto like some fixed order corrections where you actually include some of the masses in the DGLAP evolution we're doing. People have discussed this in the literature, but I don't think it has been done yet. So this is something we would need to think about. But I mean, and then all these subtleties that you're mentioning come in, we just haven't considered them yet.
Yeah, because I recall, actually from the collider part of the discussion on electric showering, there was some quite different matching schemes, whether in that step you put in mass or not, and how you put in masses. And they require different level of treatment. And I would naively assume you will get a smoother spectrum instead of the hard, shut off that I was asking earlier.
Yeah,
but
maybe,
I think there was quite some discussion in the collider literature. But
I can tell you, maybe this is what you're remembering. This may not be it, but there has been quite a large discussion on how you regulate the or generate essentially the double logs, the electroweak double logs. One, because essentially the way that this works is you can't just have arbitrarily soft W emission or Z emission because these things have mass. So you have to actually put a cutoff. Again, I'm just being schematic here. In like one way of thinking about it is you just put a cutoff on the radiation, okay? And this is what's been done by Christian and Brian in their papers. But a second way of doing it, which is what's been proposed by Anish and Wouter, is to, these rapidity regulators. Essentially, you can think about these things as being generated through the rapidity renormalization group. And so these authors here don't do this at all. They just actually implement rapidity regulators. And then in the wash, they find that their results are exactly the same. There's been quite a bit of back and forth discussion about why are those results the same? How can I understand this? And what I can say is that ultimately, if you want to go to arbitrarily high order, which for dark matter we don't, but for 100 TeV collider you might, I think that the rapidity approach is going to win, because when you go to like 2 loops, for example, the notion of putting a hard cut in somewhere becomes a bit confusing, whereas these rapidity regulators, whatever loop you're doing, you can just put these things in and they take care of things. So I think probably the more rigorous way of doing it is this, and these hard cutoffs work for our purposes, and that's what we did. And at that order, you can check that they match. But at subleading order, there are differences, and I think that ultimately this rapidity approach will win out. So I know that discussion. I've been in seminars where that's gone back and forth. Maybe that's what you're referring to partially. I've definitely heard.
Okay, thanks.